Hello friends, this is Daniel from Moralis. Today we're going to talk about Ethereum Gas. This is a topic that you guys have asked frequently in the forum, so we decided to put an end-to-end course on the subject. Though this video is entitled Ethereum Gas, the concepts we will learn apply to any blockchain that is based in the Ethereum virtual machine, EVM, such as Polygon, Binance Smart Chain, Avalanche, etc. There will be minor differences regarding how the pricing model for gas works in different blockchains, but we are going to talk about that later on. We are going to talk about gas and gas fees, how the legacy gas pricing model used to work in Ethereum, then what is the current gas pricing model and why it was adopted, and we are going to have then a technical part of the video, which is going to be about learning how to estimate gas on chain, which is as much an art as it is a science. And then we're going to learn how to estimate gas off chain through the Moralis SDK simplified tools. Let's start with the key concepts. As we know, the EVM is a decentralized computer that is powered by the miners. Mining is costly. Mining nodes are incentivized with native tokens, which in Ethereum that will be ETH, in exchange for their services. How much these nodes are incentivized is a function of gas and gas price. You can think on gas as both the fuel that powers the EVM, such as physical gas that we use for our cars, and as a unit of measure for that fuel. That will be equivalent to the way we think about gallons or liters in the physical world. Each operation in the EVM costs a given amount of gas that never changes for the same operation. So this is fixed, is described in the Ethereum yellow paper, where you can find a table with all the details. The price of gas, however, does change depending on supply and demand factors. The validators will react to this supply and demand by requiring more ETH for their services. Gas is priced, as we define, in units of the native token. ETH, for example, in Ethereum. And usually this is a measure in 1 million of the smallest amount of ETH that you can find. That will be a Gwei, so 1 million Gwei is a gigaweight, or Gwei as a short form of the name. The size of the block is a function of the entire amount of gas utilized by the set of transactions included in the block. So the amount of data that the blocks contain is not given by a measure of the data, but as a measure of the computation that those transactions involve. So how the price is defined? And this has changed recently, but before last August, that will be August of 2021, there was a first price auction model. And this is called now the legacy pricing model, which still exists in some EVM compatible blockchains, such as Binance Smart Chain. In this model, senders, or better said, their wallets, bid an amount of ETH denominated in Gwei that they were willing to pay per unit of gas. The software or wallet calculated this gas by retrieving data from recent blocks in the blockchain. Usually the wallet offered advanced options to optimize gas prices for either fast, average, and slow transaction execution. Miners on their side will sort the transactions according to the gas price bids and introduce them in their blocks accordingly. So transactions that were offering higher price per gas will be included first in the block. This happened because the miners are limited to a certain amount of gas per block, which was 12.5 million units of gas, so they are incentivized to prioritize transactions that are paying more per unit of gas, so they make more money. Miners will get the block rewards for creating a new block and the entirety of these fees for validating the network. The system depends on the user wallets estimating prices according to previous blocks. This is not always very accurate, since the demand can change unexpectedly from one block to the other. If you are unfortunate enough to put your transaction in just before one of these upticks in demand happens, your transaction most likely will get stuck in an unconfirmed state for long periods of time. So this was not very user-friendly and was one of the main reasons that this fee model was ditched. Let's take a look on a transaction in this legacy pricing model. For this, we're going to go to MetaMask and we're going to check Binance Smart Chain, which still uses this legacy pricing model. We're going to transfer some money between my accounts, and it's saying that it's Guavax, but that's because MetaMask cannot really manage native tokens when you're using a bunch of different chains. So I will send this amount of BNB to the other account. And what I want you to see is here where we have estimated gas fee. That will be the estimated amount of gas that this transaction will take multiplied by the gas price. And we are going to check the structure here. So here we can see that the estimation of gas that this transaction will take is 21,000 gas, which is the standard for transferring native tokens. And the price is 10 Gwei. This is the way that you send a transaction in the old pricing model. You could play around with this. If you send it with a lower price, most likely you will have to wait for a long time. And if you send it with a higher price, then it will just go through faster. So that was the idea, and with the drawbacks that we just talked about. Since this system had the drawbacks that we mentioned, then the Ethereum Improvement Proposal 1559 was put forward, and this is a proposal that was implemented last August 2021 in the mainnet, but was already implemented in most of the Ethereum testnets, and by now is implemented in all of them. And also it's been adopted by Avalanche and by Polygon. As we mentioned, Binance Smart Chain has not updated to this pricing model yet, and I don't know if they will ever do it. And this improvement proposal, which was implemented through the London Hardfork of the Ethereum blockchain, has three characteristics. There is a two-fee structure, which includes a base fee that goes to the protocol and a priority fee that goes to the miner. The block size is dynamically adjusted according to demand. The target size of the block is still the old limit of 12.5 million gas, but it can be increased up to 25 million gas. If the previous block is bigger than the target, then the base fee will increase to make the block size decrease back to the target. And if the previous block is smaller, then the base fee decreases in order to entice demand and make the size of the block get back to the target. The base fee is still variable, but is linked to previous block data in a very predictable way. There is an algorithm for it, which we are not going to discuss here, but you can go for it, and I will put some references in the Github repository of the lab that you can go to check, and the link to that will be in the description of the video. The base fee is still variable, as we mentioned, but we have an issue of the miners having the temptation of gaming the size of the blocks in order to increase the base fee. And that will be done by the miners colluding to produce smaller blocks. To avoid that temptation, the base fee was defined as a protocol fee and not a miner fee. So the base fee is burnt every single time. This is ETH that is going poof out of existence, which affects the ETH monetary policy. in a deflationary way, but that depends on the relation with the block rewards that this base fee might have. So it's not always deflationary, but it could be. The priority fee incentivize the miners, and what happens is that the wallet sends the transaction defining the parameters of maximum fee, which is a cap that we are mentioning here, which is the maximum amount of ETH per unit of gas that the user is willing to pay, and the priority fee, which is the tip to the miner. The protocol, upon receiving the transaction, will calculate the base fee, that's protocol business, and add up the user set priority fee. If the result is greater than the maximum amount that the user is willing to pay per unit of gas, then the priority fee will be reduced because the base fee takes priority. So it might happen that if you define a max cap that is not very generous and the base fees increase a lot, then you might have an issue. But the idea is that the wallets can calculate very precisely what will be the next base fee according to previous blocks, so they can define a reasonable cushion to manage this type of volatility and make sure that your priority fee to the miner doesn't get affected a lot by this calculation. If what happens is that the base fee that is needed for the current block that your transaction is getting in, plus the priority fee is lower than your max cap, then the excess is returned to you. The objective of this new system is to have the unpredictable volatility limited to the block sizes. So this is volatile and is very difficult to predict, but it's going to happen in the block sizes. There will be a predictable volatility that happens in the base fees. Those will vary, but the variation will be smooth and easy to predict according to previous data, and a relatively stable priority fee that will be varying very little over time. Most EVM compatible blockchains, as we mentioned, such as Polygon and Avalanche, already adopted this fee system. Now let's go to MetaMask to see an example. So we're here in MetaMask, we are in Mumbai, and we're going to send a little bit of Mumbai testnet tokens to my other account here. We'll copy that. And here we are going to paste that account, and we are going to send 0.01 Matic tokens. This is AVAX showing here because of a MetaMask issue, but don't care about that. Here we can see what is the amount. It's saying that the max priority fee is 2 Quay and the max fee is 2 Quay. This is a little bit low for my taste, so let's just put 7 and the max priority fee of 2 Quay. Let's put it back to 7 as well, just to show it. And here we are going to send it, and then we show in the actual transaction how that one went. We receive the confirmation, so we go to view in the Polygon Explorer, and we can see that here we have a type of 2, which is the new pricing model, and we can check here how it worked. The base fee was 7, which was our max priority fee, so all of the gas that we sent, all of the payment for the gas that we sent went to the base fee, and we didn't have any priority fee for the miners, but they will get the block reward anyway. And since there is not a lot of congestion in this network right now, then the transaction passed just fine. So that's the way that the new transaction model works. For the lab, we're going to start checking the contents of our Github repository. We have a front end folder, which we are going to review later on. We have our references, where we are going to check the links that we need as references for the project. Here we have the Ethereum yellow paper, which in his appendix G has the gas schedule for operations in the Ethereum virtual machine. And we have a Solidity folder with a contract and its corresponding ABI. and this is the very interesting part of this video, is that we are going to learn how to estimate gas on chain. And for this, we are going to use this contract, and those are the contents of our repository. On the subject of gas estimation on chain, this is a little bit complex because you can capture how much gas is spent at a given point in the runtime in certain function, but it's very difficult to know what happened before that function was called and what happened after. That's the part that is as much an art as a science. But we will try to give you some tools to do it. And the main tool that we are going to use is this gas left. The way that we are going to experiment with this is that we have this simple contract here. What this very simple contract does is storing a secret value for each specific Ethereum address that calls this store secret function. We are measuring how much gas we have left when we enter this point of the execution of the function, and we measure the amount of gas that was spent by the code of the function. At the end, we emit an event that will tell us what was the value of those two variables. The difference between this entry gas and the gas left when we finish is going to be our actual gas when we finish the execution of the function. We have also a benchmark function here that doesn't have any code there, and we are going to compare how that measure. This is going to be an interesting exercise to see how the estimation of gas on chain varies. We are going to copy this code to our remix, and here we are in remix, and we have the exact same code. I will expand this space a little bit more because we have some logs that we want to check out here. I will connect to injected web3. Since I have already connected my MetaMask with remix, it's not popping up at that moment, but if you have not done it, then it will pop up. Now we are going to deploy this contract, and we have our contract properly deployed here. We have here the three functions that we have in the contract. So we have the benchmark function, which is this one over here that doesn't have any logic inside itself. It's just emitting this event. Then we have the store secret, and we are going to execute first the benchmark function. So let's confirm it. We have the logs that have arrived, and here we can see that the gas estimation is exactly what was used, and we have here that at the moment of entering the function execution, we had 2,507 units of gas. So almost all of this was spent before we even reach this point, and I will explain why later. And then there is 10 units of gas here in gas spent, because basically the only thing that we did was populating this variable here, actual gas, and performing this mathematical operation to subtract these declarations. So not a lot of work in that function, and most of the gas was spent even before we reached this point. What that tells us is that there is more than 20,000 units of gas that by default are being spent when we call a function. And that is, and we pull the Ethereum yellow paper in the appendix G with the fee schedule, is this 21,000 that we have here. That's the bulk of that, is a standard amount that we pay for every transaction. When we transmit native tokens, this is exactly what we are paying. That's the reason that when we arrive to that point of execution in that function, we have already consumed almost the entirety of this amount of gas limit that we provided, as we call it. Now let's go to our store secret part, And right now, this is going to be initialized. So it's going to change from my address to be 0, which is the value that by default it has in the EVM. And we're going to pass another value, which is going to be this amount here. Not very important. We are going to submit it. So here we have this estimation, which is actually correct. And here we have the point that when we enter the execution of the function, we have still 24,000 units of gas available. The amount that we spent was around 20,000 as well as in our previous case. But here we did spend quite a few units of gas, 22,213, performing the logic of storing the secret. And that's because there is a considerable or a greater amount of gas that needs to be spent when we are initializing this variable in this mapping. We are changing it from 0 to a certain state. But if it's already initialized and we just want to change the value, even if we change it to a very big number, it's still a uint, so it's 32 bytes actually, and we check the logs. And we can see here that from 46,000 that we have as gas when we initialize the variable, we use it for the first time in regards to this address. Here, that variable had already one value, which was the previous secret number, and we're just updating it. So for updating, the amount of gas that we had to pay was less. As you can see here, when we arrive to the same point in the execution here, we have still 7,600 units of gas, and we spend only 5,000 in updating the variable. Now, let's reset that variable to be 0 again. And this is kind of like returning that variable to the same state that it will have at the beginning. And here we're going to see something quite interesting. The logs are not coming, but I think the transaction did go as expected. So we're going to inspect it here in the block explorer. Exactly the same thing. We're going to go to this area here. And here is the part that I wanted to show you. This is exactly the same thing that we were looking at Remix here in the logs. And the idea here is that the amount of gas that was estimated was the same as when we update the value of that variable with another number, but the actual gas that we spent is less. And that is because every time that we reinitialize a variable to 0, then Ethereum is going to give us a discount on the amount of gas that we pay. This refund happens also when you destroy a contract or destroy an address. And some protocols use this to kind of like offset gas cost. That will be a very advanced topic, but those refunds exist. So we have reviewed 3 different cases exactly in the same function that we could have, right? We have a case in which we have the variable being changed from 0 to a given number. Then we have a variable being updated from one number to another. And then we have another case where we have the variable being returned to be 0. You have seen that depending on what we did, we could have estimated how much gas will be spent by this function. And that estimation, if we wanted to use it in another function, maybe that comes later, that calculates something, and we want to use a previous gas estimation as a decision point. When we want to execute that type of logic, this estimation of gas becomes useful, but it has difficulties, right? We can only capture a lot of variability that will happen here according to what is the value of this variable, and that is going to be reported very accurately by this estimation of the gas that happens at this point. But regarding what happens before and what happens after, the only thing that we can do is either go to the Ethereum yellow paper and try to debug the transaction manually to see what is going on, or do certain manual testing and try to come up with a number. And we could estimate right now here that when we subtract this total gas that was spent from the amount of gas that we had when we entered the execution of the function, that number is going to be very similar every time that we run the function, disregarding what were the parameters. So let's do that calculation. We are going to pull the calculator and we are going to calculate this. So let's try in the first case, which was the initialization of the variable. We have this amount here, and that one minus this one is 21,638. If we go to the other case, this one minus this one, which is the entry point, 21,662. So as you can see, that number gets very, very, very close in each iteration that we have done. The only one where this one is going to be out of whack when we measure according to this is the one where we got the refund. And that one is because of the refund itself. So a good heuristic to do this kind of calculation is to try to estimate the greater number that you get here, and you will try to make that one a constant, and then you add your variable part that you are measuring with this gas left functionality. And it's not very precise, it's as much as art as it is a science. We are going to jump now to the gas estimation of chain utilizing JavaScript with a very nice front end that we can have thanks to Moralis. We are going to proceed right now to the gas estimation of chain. Moralis handles the front end in a very easy way, and we have here an input in our form to update our secret number. We have what is the gas estimation of storing that secret number for the current user of our dapp, and then we have two buttons. One button is to estimate the gas, and the other one to execute the transaction, which is storing the secret number. We have our current users, of course, interacting with our dapp through MetaMask, and we are connected to the Covan testnet network. Let's do this. Remember that the current status of our contract is that we have not initialize this variable, so we are going to bring it from 0 to a given number. Let's start by storing this number here, and we're going to estimate the gas. This is the gas estimation for this transaction, which is 46,000. Quite expected because we are initializing it from 0 to a given value. Let's execute it, and here we have it. We send the transaction. We have the transaction hash being confirmed. So if we go to our Network Explorer in Covan, we are going to see the estimation properly executed in the blockchain. This is our transaction, and we have here that the amount that was spent of gas in this transaction was this amount, 46,338. And that was expected. Now let's say that we want to update that number. This is going to take us less gas. Let's do 12. This is going to take us only this amount of gas because we have already initialized the variable. So let's execute this. Our transaction hash return, and we can go to check in the Block Explorer as we did before. We go to the contract interaction, we go to view in Block Explorer, And here we have that the amount of gas that was estimated by our application was exactly the amount of gas that was spent by this contract call. The last use case that we need to estimate is reinitializing the variable back to 0. In estimation of gas is going to be very similar to the previous one, but remember that here on the actual execution we are going to save some gas. So let's do it. We got our hash back, and if we go to the block explorer, it already has the transaction receipt, and here we can see that the actual gas would have been what we have estimated, but we have the gas refund because we are resetting the variable back to 0. We are going to learn in the code how you can estimate your gas off-chain using very little JavaScript, and also how to execute a transaction very easily using the Moralis SDK. Remember that this kind of workflow might be needed in case you need to have some gas estimations for the flow of your dapp. If you only need to send a transaction, then the MetaMask or the wallet software that you're using is going to actually estimate the gas for you, but that's only when you send the transaction. If you don't want to send the transaction and want to wait until certain conditions are met regarding the state of the blockchain that will allow you to have certain gas expenditures, and that really depends on your use case, that's when this part that we're going to learn is going to be very useful to estimate the gas expenditure off chain. Let's go to it. To build this little front end, you need a very little elements. You need, of course, your HTML base, which I have here, only has a very basic layout where we have the inputs that we're using for entering our secret number and for showing gas, and the two buttons. The bulk of what we're doing is in these buttons, which are calling a function estimate to estimate the gas, and store secret to execute the transaction that stores the secret number in the blockchain. We have for that used the logic.js that we are importing here, along with the Moralis SDK. Let's get to the logic file. Here we will need certain elements. To begin with, we need the address where our contract was deployed, and this is very easy to get. I will go to the browser here, and if you are in Remix, where you most likely will deploy the contract as I did before, you are going to be able to find your contract here, and then when you deployed it, actually it will show here under deployed contracts, and you will have a very convenient interaction here to copy the address. So that's one part that we will need. The other part is the API, which we have here. I will hard code that element in the Github repository that is in the description of the video, so you don't have to manipulate that one. But if you need to get it, it's very easy also to get it from Remix. You have to go to the compile section, which is here, and when you compile your contract, you will get this interaction here to get the API. So that's also quite convenient. Now, the other things that you will need are these two. This is our access to our Moralis server and our application ID, and for that you have to have access to Moralis. If you are not a member, it's very easy to sign up. You just need to sign up totally for free. If you are already a member, just log in and create your server. And since I'm already a member, I can just log in. And here I will see my servers. I have the current server that I have here that I will use for this demo, and then in my details I have my server URL and my application ID. You are going to be able to get these details in the server that you are going to create. When we have these elements, our Moralis access and our contract and API, we can proceed to explain the code. What we have here is very simple. We have just a login function which enable the Web3 instance with Moralis and makes sure that we are in the Koban testnet, which is the chain ID of number 42. This is 42 in hexadecimal values, so that's the reason it is like this. And regarding the functions, we have only two. We have one function to estimate gas and one function to store the secret. Both of these functions are interacting with our contract, so they generate a contract object in their own specific way. We have our function estimate here that enables a Web3 instance and then creates the contract in this line over here. We are creating a contract object by providing the ABI and the address of the contract. The line just above is just collecting the value of the secret number that we are wanting to store from our HTML document, and then what it is doing is just calling the store secret method of our contract and provide the secret number that we are getting from the HTML document. But instead of executing a function or making a call or transacting, what we are doing is just estimating gas. These parameters here are quite important, because if we don't send the actual address that we are executing this transaction from, the estimation is not going to be exact, because the Web3 library is not going to know who is executing the function and will give us a general estimation that will be very similar to the kind of estimation that we get when we are initializing the variable, because that's kind of like the most general case. If all of these steps are completed, then what we are doing is just populating the space in our form with the estimated gas. So that's what we have here, just a population of our HTML form element with the value of the variable that we just calculated here with the estimate gas function of the Web3 library. Now, for executing the function of storing the secret, here we are utilizing Moralis, which is a very convenient way of executing smart contract functions without doing a lot of encoding. So we're just providing here our Web3 instance and certain options: the contract address, the ABI, the function that we're going to call, and the parameters. And with this, we're just calling this part of the SDK, this function inside the SDK that's called execute function, with these options, and that will just send the transaction in our behalf. And when the transaction gets the receipt, is going to return it here in the alert that we were looking at before. So this is quite simple. I have my server already running here, and this is what we were taking a look before. I will populate the variable again. This is this amount of gas because we're reinitializing the variable, and now we're going to execute it. We got our transaction hash, and let's go to the MetaMask to grab this contract interaction. We see it in the block explorer. We got the transaction receipt, and we have the gas spent, which is exactly what we estimated. Friends, I hope that you have enjoyed this full course on gas. We cover all the theoretical components of gas, how gas is used in the EVM compatible blockchains, how gas is accrued for the operations that we execute, and how gas is priced in the old legacy model and in the new pricing model of gas prices. We also cover what networks adopted already the new model after the London Hardfork, and also we mentioned the blockchains that are still using the legacy model, which is Binance Smart Chain. Also, we perform gas estimations on chain and also off chain. I hope that all this knowledge serves you well. See you in our next video.